Hello, now we are going to discuss the nonlinear electron oscillator model. This is a model which is a generalization of the Lorentz model that we had learned earlier that governs the atom-light interaction. Now again, let me repeat myself. This is not a model for the atom, but it's a model that captures the atom-light interaction. So think of it this way. You have a nucleus, a positive charge and electron, and there is a equilibrium position where the electron would like to be. And beyond this equilibrium position, once you drive this system with an external electromagnetic wave, it is the electric field that couples to the charges. So what it generates is induces a dipole moment, which is basically moving the electron away from its equilibrium position. And such an interaction leads to, from the atom itself, a restoring force which tries to bring back the electron to its equilibrium position. Such a force is what is indicated here. So I'm writing down the Newton's equation of motion. So you have essentially the second derivative of the displacement, right? So look at equation number 1. The second derivative of the displacement, and then there is this restoring force term, omega naught squared x. Then you have the external drive, which is indicated by this E of t, which is the amplitude of the electromagnetic wave. Now remember that the displacement is along the direction of the electric field. So the induced dipole moment is along the direction of the electric field. So we will, in our further discussion, we might periodically drop the vector direction, but we know clearly that it is along the direction of the polarization of the incoming field. All right. So remember that omega naught square, this is a positive definite quantity, and it is related to the spring constant divided by the mass of the electron. And such a force can always be obtained from a potential which is given so, right? V of x is half ks times x squared. So this is a harmonic potential, and you can clearly see that this potential at x equal to 0, there is a minimum of this potential, and the force is given as a negative gradient of the potential. Now this is the situation for the linear Lorentz model. This is what we have learned. We have looked at the solutions of this earlier, so I will not dwell beyond this. So what is different in the nonlinear model is that we are now looking at a much stronger excitation. That is, my source term here, E of t, has got a much larger amplitude. That is what I mean by strong excitation. So once you do that, the potential no longer remains to be quadratic or harmonic. One needs to add higher order corrections to such a potential to accommodate for this large or strong excitation. So in the simplest terms, what I do is add a few more powers to the word potential. My V of x now becomes half kx x squared, the original harmonic potential, plus a correction term with capital A x cube, and another correction capital B x to the power of 4, and so on. So this is the way to add corrections to the potential. There is another way to view the same thing, which is let us undertake the Taylor series expansion of V of x about the equilibrium position x equal to 0. So recall that my equilibrium position was indeed where the force is 0, which is at x equal to 0. So if you look at the Taylor series expansion, I have got my V of x, which I'm expanding about x equal to 0, the equilibrium position. So I have got V of 0, which is the first term, the function and its value at that point where we want to expand. And then you have the next term, which is x times dv over dx. So this derivative term is calculated again at x equal to 0. Then the next term is x squared by 2 factorial, second derivative of the potential with respect to x, and x cube with 3 factorial, and the third derivative with respect to x, and so on. So now let's understand each of these terms term by term. So if you look at the first term, the V of 0 is simply a shift in the total energy. Such a term is of no consequence to the force, because if you recall, the force was actually the derivative. The force was basically a change in the potential as a function of x. So a constant addition or subtraction is not going to do anything other than shift the scale of the overall energy. The second term involves the first derivative of the potential with respect to x, and you can clearly see that we are talking about the equilibrium position at x equal to 0. Hence this term dv over dx, which is the negative of which is proportional to the force, is indeed 0, and hence the next term also is irrelevant to our discussion. So this term actually goes to 0. The first term is irrelevant. Now let's look at the next. This is the term that we had retained in our linear harmonic oscillator model. And you can clearly see that the half factor is there coming out of the Taylor series expansion. The d2v over dx square is essentially related to the spring constant, or in other words, mass times the natural frequency, which is omega naught square. So this is positive definite. This being positive definite implies that the equilibrium position was a minimum, or rather we are talking about a stable equilibrium position. In case of unstable equilibrium position, this would have been of a negative sign. All right. It is this force that governs the binding of the electron harmonically to the nucleus, and this satisfies the Hooke's law, right? So that is, if I make small detours away from the equilibrium position, I will be pulled back to the equilibrium position, which is at x equal to 0. Next non-trivial term, so this I will call it as a linear term, and it is the non-linear term which is of most interest. So you see that in this non-linear term, the first correction to this to the linear oscillator comes from this x cube term. And remember that we had just put in, we had written the correction earlier as simply a times x to the power of 3. So you see that I can clearly identify my a, which is simply 1 over 6 times the third derivative of the potential with respect to x taken at x equal to 0. So, this is the way to think about these corrections, sort of a generalized force, okay, which has this additional nonlinear terms, right, which actually now drive my original linear harmonic oscillator. So I can rearrange this in a particular manner. So you see, I'm looking at the same equation number 1, but now with including these generalized force, right? So now what I get is the first term, which is the second derivative in space coming from acceleration. Then you have the restoring force coming in here, right? And then you have the first correction term, and then you have the next correction term, and so on and so forth, driven by the electromagnetic field, where the electric field is driving the dipole moment. So E is the charge, m is the mass of the electron, and capital E of t is the electric field associated with the electromagnetic wave. So now what we want to do is we want to solve this nonlinear equation and come up with a solution. So there are multiple ways of doing it. One is a perturbative solution to this nonlinear oscillator equation. So now let us compare. So my harmonic term, or the linear term, is the second term, right? This term. And I'm comparing the linear term and the nonlinear term. Clearly, if I want to implement a perturbative solution, my nonlinear term better be small in comparison to the linear term. Or rather, one is talking about displacements, which you can arrive from this, such a way that these are smaller than a particular combination. That is, it is smaller than m omega naught square by 3a. So that is the kind of regime that one is talking about. So in other words, nonlinearity is weak. Hence, we are going to now solve it in a perturbative manner. Now, remember that even this nonlinear term becomes apparent only if you necessarily drive the system with larger and larger displacements. And this happens when you apply larger and larger electromagnetic field, or the amplitude of the electromagnetic field is large enough. So now, of course, we are going to look at this solution in the spirit of Born approximation. So what I will do is I limit my nonlinearity to the very first term. So I consider this as my equation number 4. So I have the acceleration term, I have the restoring force, I have the first term, nonlinear term, and I have the drive coming from the electromagnetic wave. All right. So the spirit of Born approximation is such. What we do is basically the following. In the very zeroth order, or the first approximation, we ignore the nonlinearity, right? So by ignoring nonlinearity, what it means, I set this little a, the small a, to 0, and then I obtain a solution which I call it as x1t, meaning the one in the brackets stands for the first approximation. Then what I will do is, in my second approximation, in my next higher order correction to that, I will put in this solution x1 of t, which came about because of ignoring the nonlinearity, plug that back in as sort of a source term, and solve for a higher order correction or higher order term, which now is a better solution to the nonlinear equation than the x1 of t. And one does this procedure systematically. And by the way, as you keep doing it, you will see clearly, as I will show you now, that one will start generating multiple higher order overtones of the fundamental frequency omega, where omega is the drive. So again, of course, let me point out, we are looking at equation number 4, where omega naught corresponds to the natural frequency of oscillation of the oscillator, whereas omega, which is distinct from omega naught, is the frequency of the incoming electromagnetic wave. So you see that in steady state, essentially, one is driven by the drive frequency, which is omega. All right, so let us undertake this step by step. So let's look at the first approximation. So here you see in equation number 5, what I'm doing is I'm ignoring the nonlinear term. So this is what we had done earlier, and we get a solution which I'm writing down again. You can quickly recall and look at your old notes, and you will find the solution looks like this. So you have essentially the drive term. So within the bracket times half is going to give you this cosine omega t, which is my drive. And you see that there is a resonance term, that omega equal to omega naught, this is going to blow up. Remember that I have ignored any relaxation processes in my system, but in reality there will be relaxation, and that gives a complex term that is added to it. So remember, in our earlier calculation, we would have had a I times gamma omega kind of a term, which would have been there, which we have ignored. So let us not worry about that. So you see, what you have is x1 of t now, which is my solution after ignoring the nonlinear term, and I get this nice resonant kind of behavior. Now remember that my differential equation, which is equation number 5, is actually a inhomogeneous differential equation. So I have got two solutions, and the total solution is a superposition of these two. The first part is a homogeneous solution, and the second one is an inhomogeneous solution. Now if you quickly recall, the homogeneous solution actually would decay given any realistic relaxation process. The homogeneous solution will damp out to 0, whereas the steady state solution, which is what I have written down here, or the inhomogeneous solution, is basically what is being driven at the drive frequency. So you can clearly see this exponential plus minus I omega t kind of dependencies which are there. This is what is the steady state solution in time. And the way to obtain this inhomogeneous solution is to, we have done that even earlier. You look at such an ansatz that the solution goes like alpha times exponential I omega t, plug it back in the differential equation 5, collect the terms, and you would get this this inhomogeneous solution. Of course, there is something very nice. If I look at the linear equation and if I look at the inhomogeneous solution to the linear equation, if I find a solution, then mathematics guarantees me that that is the solution. So if I found the solution, then that is the solution of the differential equation. All right. So now that we have got the linear term, what I'm going to do now is solve my nonlinear equation to the first Born approximation. So again, so let me look at the differential equation again. So I have got the usual terms, the acceleration term, the first one. Second one is the restoring linear term. This is my source drive. And you see now I have put my nonlinearity on the right hand side, right, as sort of a source where I'm using x1 square, where x1 was the solution of the equation of the above equation where I had ignored nonlinearity. So you see now clearly I have got a drive. So now imagine, so look at these source terms, right? I have got a drive which is at omega frequency. I also have a drive at twice omega because it's x1 square, it involves a square. Not just that, I have actually three kinds of drives. The x1 square involves a square of this particular equation number 6. So you see I need to take a product of this. So I have got plus I omega t, minus I omega t, and all combinations thereof. So essentially what I get is basically three frequencies, three terms. I get omega plus I omega t minus I omega t giving rise to a DC kind of a drive. That is this oscillator now is being driven at zero frequency. Then I have got plus I omega t times plus I omega t give me twice omega t, and similarly the complex conjugate which is at minus 2 omega t. So you see what again I have got is essentially I have got a DC term drive and a drive at 2 omega. And this is again I am doing the same exercise seeking the steady state solution of this driven oscillator, where now I got a drive which has got a 2 omega as well as DC drive. So essentially what I get, again using the similar technique and equating the various frequencies, what I get is basically three terms. This is my equation number 7, which gives me three terms for the nonlinear solution of this above equation number 6. All right. So what is the nonlinear solution? It has got a DC term. You've got a response which is DC, which basically depends on the intensity of the light. Remember that this is omega square. And again, important to note that this DC term, the value of it actually depends on whether omega is close to the natural frequency or not, right? So omega equal to omega naught, one does get, that is if my drive frequency is matched with the natural oscillation, in that case I would get a very large DC response to my because of this nonlinear drive. The second term is of course sort of familiar, where you have the linear system, the linear term. So there is little difference between the original linear term and this one. And remember that there is a factor of 2 that I have written down here in this denominator of e by 2m. And then you have the next nonlinear term. So the first DC term was a nonlinear term. Similarly, the next nonlinear term right, which is this, is being driven at twice omega, right? We are, because of the nonlinearity now, even though I'm coming with an electromagnetic field at omega, I'm getting a response at twice omega, okay, which again is resonant to omega naught being equal to 2 omega would be the resonant condition in which this term uh, basically uh, this term would dominate at omega naught equal to 2 omega. Even though I came in with a field at omega, which is at optical frequency, I get a response at DC, which is at 0 frequency. I get a response at twice the optical frequency, which is, by the way, what is called as, what we will see will actually lead to something called second harmonic generation. So it is actually quite dramatic in a lab, where you put in, for example, in an Nd:YAG laser, you get a 1064 nanometer infrared light, and then you put it through a nonlinear crystal, okay, which has this non-zero nonlinear coefficient chi2, and then by appropriate alignment, which we will discuss soon, we start getting very bright green light at 532 nanometers.